Hello, in this meeting, meeting 10. So in this meeting, we will cover wireless communications. Okay. In the last meeting, we talked about the internet and the protocols that are used in the internet, the TCP/IP standards. Okay. The layers. Okay. The layered architecture for this network of networks. So let's revise some topics about the last meeting. Okay, tell me what is the layer for the TCP protocol? TCP, it is related to what layer? To what layer? TCP. Sorry. Yes, good, Sadia. It is the transport layer. Okay. So the transport layer will create a virtual circuit in which it will negotiate with the transmitter with the receiver about all, okay, the requirement for this connection. Okay, so in the first we will have the 3 handshake connection. Okay, 3 ways. We have request to connect, we have the answer, okay, yes or no, and we have the acknowledgement. After that, the connection is established. Okay, so the transmitter will send all the data to the receiver. Okay, and the receiver, once it gets the data, it will acknowledge this data. Okay, to go further. Okay, other data. Okay, once the transmitter does not receive any acknowledgement about the received data, it will retransmit. Okay, again. Okay, once all the data is sent, so the connection will be closed. Okay, so this is the TCP. Okay, for the IP, it is the protocol of what layer? The IP. The IP, the protocol for what layer? Yeah, the internet layer. Good. Okay. So what is the role of the IP or the internet protocol? The IP address. What is the role of the IP address? It is the identifier of each device or each computer, okay, in the internet. Once you are connected, so you are identified by your IP address. Okay, without IP address, you cannot connect. You cannot join these networks. Okay. Okay, so let's start now with the wireless communication. So in this meeting, okay, we will see the decrease of power in a radio signal with distance traveled. Okay, we will see how to prevent interference between wireless signals. Okay, because we have wireless signals, we have shared area. Okay, so we will have some interference. Okay, so how we can prevent this interference? Okay, between wireless signals being transmitted simultaneously in the same time. How to cover a binary bit stream into a form suitable for radio transmission. The detection and correction of errors. So you see, you can understand that there will be some errors while sending these bits, okay, these codes. So we need some detection and correction algorithms, okay. The two short-range wireless data transmission technologies, we will see the Wi-Fi and the Bluetooth, some characteristics of the Wi-Fi and the Bluetooth and what is the difference, how to keep systems secure from accidental or deliberate damage, okay. So we will start by attenuation. We have already seen that the wave, okay, or the signal, okay, will have some attenuation, will have some reduction, okay, as it travels away from its source, okay. So if the source is here, okay, when the signal travels over distance, okay, away from here, from its source, so it will be attenuated, it will be decreased, okay, it will be reduced, okay. Any wave, water, sound, or electromagnetic attenuates, dies away, okay, it will die at the end of at some distance, okay, with increasing distance from the source, okay, when it will travel away from its source. So the distance, the wave will be attenuated, will be die, okay. Attenuation is the reduction of the amplitude of a signal. This is the amplitude of the signal. So you can see that the amplitude decreases, okay. The amplitude decreases, okay, until it will be equal to 0. Attenuation may appear to be a serious disadvantage to wireless transmission, and we see that we have some regeneration, okay. It will regenerate the signal to not be lost, okay. So look here, figure 2 shows how the power spreads after transmission. So you can see here, this is the power, okay. This is the power of the signal. After that, this power will be divided by 4. After that, it will be divided by 9, etc. Okay. So after traveling a particular distance, d equal to 1, the power in the wave is spread out over the area indicated by the curved square. Okay. So this is the curved square. Okay. This is, imagine that this is the power here of this signal here. So after distance, okay, when distance is equal to 2, the power here is divided by 4, okay. And when the distance is equal to 3, the power is divided by 9. When the distance is equal to 4, tell me how much? When d is equal to 4, so here we will have how much? We will have 16, okay. So you can see here d power 2, d power 3, okay, d power 3 power 2, okay, d the square of the distance, okay. So after twice the distance d is equal to 2, it is spread out over an area over times the size, okay. So you can see that over an area over here 4 times the size. After 3 times the distance d is equal to 3 over an area 9 times the size. So the same receiving antenna at a distance d is equal to 2 picks up 1 divided by 4 of the power of that at d is equal to 1. So you can see here, when you are here, you will receive a signal with power, okay, with this power, okay, with power P here, okay. But when you are at this distance, okay, you will see a signals with power divided by 4. This power divided by 4. When you are here at distance is equal to 3, so you will see a signal with power is equal to power divided by 9. Okay, this power divided by 9. Here at D is equal to 4, this power divided by 16. So you can see that the power of the signal will be attenuated, will be decreased. Okay? Is it clear? Clear? Is it clear? Okay. So the same receiving antenna at a distance D is equal to 2 picks up 1 divided by 4 of the power that at distance is equal to 1. And at distance is equal to 3, it is equal to 1 divided by 9. So this is known as the inverse square law. It is called the inverse square law. Okay, so the received power is proportional to 1 divided by the square of the distance. Okay, so you can see here, when D is equal to 2, 1 divided by 4. When D is equal to 3, 1 divided by 9. When D is equal to 4, 1 divided by 16. Okay, this is the power. Okay, will be attenuated, will be divided by this number. Okay. So the question here, what fraction of the power would be received by the antenna at D is equal to 4? So the fraction is 1 divided by the square of 4 is equal to 1 divided by 16. Okay, tell me when D is equal to 5 now. What is the fraction? When D is equal to 5, what is the fraction? When D is equal to 5. Tell me, 25, good. 1 divided by the square of 5 is 1 divided, no, it is not 25, it is 1, the fraction is 1 divided by the square of 5, it is the 25, okay? So, there is additional attenuation introduced by the atmosphere, introduced by the weather conditions, introduced by the topographical features of the nature terrain, okay? Artificial objects such as buildings or traffic and so on, okay? So this is one of the examples, okay, of the attenuation. Why we have attenuation? So this is, it is a cause of this atmosphere, okay? The atmosphere, the weather condition, the topographical features of the nature, mountains, hills, okay? All these features, okay, natural features will have some attenuation of the signal, okay? So this is why when you are in some places when there are many topographical features of nature, or when there are some buildings, okay, that are very high, okay, so you will have some troubles with the connection, okay? Why? Because the signal itself will be attenuated, and the need for regeneration of this signal is very important, okay? Is it clear? Clear? Do you have any question? Any question? Okay. Okay. So measurements of such situations have shown that in urban environments, an increased power law of 3 or cube or 4 is a good representation. Okay, it is not just this, the inverse of the square. It can be the inverse of the 3 of the cube or of 4. Okay, why? Because in urban environments we have many buildings, we have many traffics. Okay, we have many obstacles for this signal. Okay, so the signal will be reduced يعني enormously. Okay, hugely. Okay, so here we can have 1 divided by d cube. Okay, or 1 divided by d power 4. Okay, it is not just the square of the distance. Okay, so for an inverse cube model, the received power would be proportional to 1 divided by the cube of d, and for an inverse fourth, okay, power, so the received power will be proportional to 1 divided by d power 4. Okay, so is it clear how we can decide if it is the 1 divided by the square of d or the cube of d or the power 4? Okay, it is related to the place. Okay, to the attenuation, to the obstacles that you have in this place. Okay, so attenuation now can be advantageous for wireless communications. How it can be advantageous? How we have this attenuation. Okay, so the signal will die after some meters or okay, from the source. Okay, this fact can be advantageous, can have some benefits for the wireless communications. How it can be? So the attenuation means that beyond a certain distance, okay, after a certain distance, devices operating on the same frequency band will not interfere with each other. So frequencies can be reused. Okay, so once we have this frequency, so here after this distance, I can reuse the same frequency. Okay, after this distance, I can reuse this frequency. Okay, why? Because the signal will die and I don't have here interference. I will not have interference. Okay, so many signals, okay, that will interfere, that will have some conjunction. Okay, so in mobile telephony, this feature is exploited by dividing the area of service into cells. Okay, this is the origin of the term cellular telephony. Why we called it cellular telephony? Because the area will be divided into cells and each cell will work on one frequency. Okay, and we can use this frequency after some distance. Okay, so we can use, so this is the advantages of the attenuation. Okay, do you understand that the attenuation for wireless communication can be advantageous? Why? Because because the signal will die after some distance, so I can reuse the same frequency and I will not have interference. Okay, so this is what is called the cellular networks. Okay, so as you can see here, the cells are clustered together to enable frequency reuse. Okay, so this is the cell. Okay, so if you have here this okay, this is, for example, one cell. Okay, this cell, this 2, this 3, this 4, 5, etc. Okay, so we can have cells in a highly populated area. You can see the dimension of this cell. It will differ from one country to another, from one area to another. Why? It is related to the population. When it is populated area, such as the town center, so the cell will be smaller. Why? To allow for a larger number of users for a given area. Okay, So these frequencies can be reused after a sufficient distance to avoid interference. It is the positive feature of attenuation. Okay, it is to avoid interference when you use this. This feature, okay, of attenuation. Okay, is it clear? Any question? Yeah, each cell will have limited range. This is what is called limited range. So this is the range of the signal that will attain. Okay, after this range, the signal will disappear. Okay, so we can reuse this frequency again. Okay, and you can see that this is the difference. Here we have some downtown. Okay, downtown. So it is populated. Okay, there are some here number of users. Okay, will increase in the downtown. It is not as in the countries. Okay. Okay, so look at figure 4 now. The figure 4 shows transmitters at a particular frequency that are separated by two cells using different frequencies. Now you can see here, okay, in this huge cell composed by 7 cells, okay, we can reuse, okay, the same frequency. Okay, so you can see here, this is F1, the frequency 1. It can be used after 2 lines, okay, 2 lines of cells. This is F1. F4, it can be used after 2. This is F4 after 2 lines. This is the line 1, the line 2. It can be used here, okay. This is F3, the same. F2 for F2. This is line 1, line 2. Okay, so this is F2. F1, it is the same. It is separated by two lines of cells, or 2 cells, in fact. Okay. So the figure shows 4 adjacent 7-cell clusters. So this is the first. Okay. This is the second. This one is the second 7 cells. Okay. This is the third here. And this is the fourth. Okay. Sorry. So each has a base station operating on a particular frequency built from F1 to F7. Okay, so here you have in each cell, okay, you will have some base station that will operate at this frequency. Okay, so the signals of this cell, okay, will not be interfered with that one, okay, because they will operate in different frequencies. Okay, but after 2 lines or 2 frequencies, I will reuse this frequency because here the signal already sent from this cell disappear after these 2 distances. Okay, so I can reuse, okay, it. Okay, now we move to the, okay, do you have any question about the attenuation? What does it mean? What is the advantage? Okay, is it clear? Clear? Okay, I need the feedback from all of you. Okay. Okay, clear. So move now to the digitization and modulation. Now we will discuss how to convert a binary bit, okay, stream into a form suitable for radio transmission now. Okay, so now we have some bits and we need to send these bits, okay, these bits to the receiver using radio transmission, using wireless communications. So in order to represent the analog signal sufficiently, as well as a string of numbers, okay, these binary numbers, it is vital that two conditions are met. Okay, so we have already seen that how to convert one analog signal to digital one. Okay, there are two steps that we need to follow. Okay, so the signal must be sampled sufficiently frequently in order to represent all its significant fluctuations. It is called the sampling. Okay, so I will divide my, okay, I will take many samples from my analog. Okay, so this is your analog. Okay, it is a continuous signal. Okay, what does it mean, an analog? It is a continuous signal. It can be the temperature, it can be the pressure, the speed of your car, whatever. Okay, the factor that you need to measure. Okay, so you need now to take some samples. Okay, so I need to take, for example, samples from here. This is another samples, another one. Okay, another one here. We need what? We need to take a huge number of samples. Why? We need to take a huge number. Why? Tell me why we need to take, okay, samples sufficiently frequently. Sufficiently frequent. Okay, why? Why we need to take many samples? Why? To represent all fluctuations. Okay, to represent all these fluctuations. Okay, because when we take some, okay, samples, so the shape of the fluctuations will be lost. Okay, and I cannot regenerate or recover my signal at the receiver. Okay, I will have some corruptions, some errors, okay, at the receiver. So I need from the first two samples, okay, to do the sampling in a good way. Okay, so this is what does it mean in a good way? We will take sufficiently frequently, okay, samples in order to represent all significant fluctuations. Okay, once now we have these samples, okay, the samples must be coded now using a sufficiently accurate and precise number for each sample value to give a digital representation close enough to the original analog value. Okay, this is called quantization. Okay, so do you understand that? It is the quantization. What does it mean, quantization? It is the fact that from these samples it will be coded, okay, with accurate and precise number. Okay, so we need, for example, we need here three bits. If we need 3 bits, okay, 3 bits, so we will have 0, 0, 0, we will have 0, 0, 1. So we will have how many levels? With the 3 bits, we will have 2 power 3 levels. It will be equal to 8 levels. Okay, so I can, for example, these samples can be represented using 8 levels. If I see that 8 levels will not be close sorry and will not be sufficient for these samples, I can use 4 digits. Okay, so I will have 2 power 4. It will be equal to 16. Okay, levels. So 16 levels will show all the differences between these samples. Okay, and so on. Okay, let's start by sampling now. So see this sampling. Figure 5 shows a segment of an audio signal. Okay, an audio signal is an analog system signal. Okay, So the horizontal axis represents time. This is time. Okay, this is the time. In figure 6, the signal in figure 5 is sampled. Now I will take samples from signal, this signal, by these points, okay? Sufficiently frequently, you see that it is sufficiently frequently. You can see that all the fluctuations in the signals are sampled, okay? I have many samples that will represent all these fluctuations, okay? So imagine receive sample values and simply joining the dots smoothly, okay? Imagine you will have the perfect, okay, the same signal, okay? So you can see that, okay? Quantization now, turning to quantization. So to left half, to left half of the figure shows the quantization intervals of the 0.25 units. Clearly, a lot of detail is lost. Clearly, see, you can see that when you use here only 3 bits, okay? Here we have how many levels? We have this level 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 levels. Okay, here, but here you can see how many levels. Okay, so each level is divided by 4. Okay, we will have more than 32 levels. Okay, so all here you can see that all these fluctuations or these samples can be represented, okay, with sufficient way. Okay. Okay, so this is what is called, okay, a good representation of the original signal. Okay, why? Because here we have many quantization levels. As far as we have many quantization levels, we will have a good representation of the original signal. Okay, is it clear? Any question about sampling and quantization? Here we will have more than 32. Look, here we have 8 levels, and in each one we have 1, 2, 3, 4 levels. Okay, so we will have here 2 power 5. Okay, 2 power 5, it will be equal to 32 levels. 32 levels. Okay, so we will have many quantization levels. Okay, you can see here this point can be, okay, good, but this point, look, this point and for example, you can see that, for example, this point with this point, it is the same level. Okay, and this point, if you have here point here and this point with the same level in this chart, but in this chart, no, level different, because we have many levels, okay, that will recover or that will sufficiently represent all these samples. Okay, okay, is it clear? Move now to the Wi-Fi and the Bluetooth technologies now. So these two technologies for short range. What does it mean, short range? We will have some meters to cover, okay? These technologies, the Wi-Fi and the Bluetooth, will cover a distance, a limited distance of coverage, okay? We cannot use your Wi-Fi after 1 kilometer, for example. It is very difficult to do that, okay? Even if you have a strong router Wi-Fi devices, okay? It is the same for the Bluetooth. You have some meters, okay? Just some meters. After this, for example, 100 meters, you cannot join using the Bluetooth. So these systems typically use low power transmission bands over distances from less than a meter to 100 meters or so. Okay, so you can just use some distance from 1 meter to 100 of meters. Okay, the Wi-Fi operates either in ad hoc or infrastructure mode. Okay, but the Bluetooth connects individual stations using one or more piconets. So these two technologies will be discussed in more details in the following. Okay, so this you can see here. Even these technologies are working in a short range. Okay, the wireless data transmission. They operate at different technologies. Okay. Okay, so the Wi-Fi operates in ad hoc or infrastructure mode, and the Bluetooth will operate at piconets. Okay, so we will see that. Okay, so let's start by the Wi-Fi technology now. This is Wi-Fi technology. So the Wi-Fi is a name given to wireless local area networking, the WLAN. Okay, the wireless local area networking technology that is complete with the IEEE 802.11 family of standards. Okay, so here you will have many families. Okay, you will have a lot of families in the Wi-Fi. So give me some examples of this Wi-Fi family. Examples. Examples of these families. You don't know? Examples, Wi-Fi 6? No. This is this family, We need this family. What does it mean? This family, yes, they will work at different frequencies, okay? But the names will differ, okay? It is not like a yes, good, Ahmed, good. Yes, it is A, B, C, D. There are E. Okay, it is there. These are standards. Okay. So the IEEE. What does it mean? The IEEE. It is the Institute of Electrical and Electronic Engineering. Okay. So all the communication networks, wired, wireless, satellite, WiMAX, each standards are written by the IEEE. Okay, so for the okay, so we will have many standards. Okay, so as Ahmed says, we will have 802.11a, .11c, b, d, and e. Okay. Okay. So this Wi-Fi enables devices such as computers, printers to be wirelessly connected together to form a local area network. So the Wi-Fi networks now are also used to enable mobile devices such as laptop computers, mobile phones to connect to the internet. Okay, so this application is now common in public places such as the airport, the coffee, with a reach up to about 100 meters. Long distance systems are also possible, operating over several kilometers. Okay, so in the wireless local area networks, the nodes that can be laptops, that can be mobile phones, that can be routers, switch, okay, etc., are usually referred to as a station. Okay, it is called what? It is called a station. So acknowledging the fact that each communicating device acts as a radio station with a transmitter and a receiver. In each station, the connection to the network is provided by a wireless network interface card how you can connect to your network. You need some wireless network interface card, the NIC, okay, to connect to your internet, to connect to your, okay, to your network, okay. Without this card, you cannot connect, okay. So this is why some in some computers, desktop computers, we can add this card, okay, like a USB, okay, with a USB port, okay, to add this feature to this desktop computer, okay, computer desktop, okay. Why? Because they are not, this network interface card is not embedded in its components, okay. So we can add this component. A Wi-Fi network can be configured in one of two these modes. So it can be an ad hoc mode or an infrastructure mode. Okay, let's begin by the ad hoc mode. What does it mean ad hoc mode here? In the ad hoc mode, the stations communicate with each other directly without the need of any intermediary or central control. Okay, so imagine you have this here, your mobile, this is mine, this is yours, okay. We can communicate, okay, without, okay, I can communicate with, for example, Sadia, okay, directly, okay. Sadia can communicate with his friends, with her friends, sorry, Rima, okay, directly, okay. I can communicate with Rima directly, etc. Okay, so we don't need any intermediate or central control. Okay, we can communicate directly. This is the ad hoc mode. It is called the ad hoc mode. In the ad hoc mode, we can communicate directly. We don't have any central point, any station point, okay, base station or whatever, okay. So this means that when one Wi-Fi device comes within range of another, a direct communication channel can be set up between them, okay. This is a direct communication channel between these 2 points. This is a direct communication point channel, okay. So they can communicate directly without any needs from the other, without any help from the others, okay. Now, so the figure 8 shows an example of the geographical layout of a network in ad hoc mode. The dark circles represent Wi-Fi stations, and the concentric circles around them represent the wavefronts of the radio waves. Okay, so this is the range of these. Okay, the coverage of this phone. Okay, once we have some interference between these two mobiles, so they can communicate. Okay. So assuming each station is in range of all the others, all communication pairs are possible as a fully interconnected mesh. Okay. Okay, move now to the infrastructure mode now. The infrastructure mode. Okay, so give me some examples about the ad hoc mode. So the manets is an example of the ad hoc mode, okay? The mobile ad hoc network, the mobile ad hoc networks, okay? And the VANETs also, the vehicular ad hoc networks is an example of the ad hoc mode, okay? So move now to the Wi-Fi technology. In the infrastructure mode now, stations in infrastructure mode communicate with each other, but via a wireless access point, okay? they cannot communicate directly. They need some point, okay, access point. So that acts, this point acts as a connector between a wired network and the wireless network, okay, between a wired network and the wireless network. Okay, so this is your wired network, okay, and this is your access point. So imagine, for example, you have in a faculty, okay, in your faculty, okay, we have already the infrastructure, okay, you have wired networks, okay, and for each department there will be some access point, wireless. Why? To be wirelessly and connected, okay, for your mobiles, for your laptops, etc. So this is our mobiles and our laptops, okay, and we will connect to the network of the university using this access point, this wireless, okay. So this is an example of infrastructure mode. Also, all about the coffee in your in the coffee in the, for example, airports, or this type are the infrastructure mode. There are some Wi-Fi point, access point, okay, that you need to connect, and this access point will, okay, connect to you to the network using wired, okay, network, okay. So the access point is effectively a base station that control the communication between the other stations, okay, and each station exchanges information only with the access point, okay. If you need to communicate with others, so you will communicate with this access point. This access point will forward your will communicate with the other networks, okay, using these wired network. Okay, is it clear the difference between the access point, the ad hoc mode and the infrastructure mode? Is it clear? Any question? Clear? What about the others? Where are you, Saif, Reem, Marah, Faris, Abdullah? Where are you? Okay. Okay. So the access points now form part of a wired network infrastructure and are not mobile, okay. It cannot be a mobile, it is a device, okay, that is destined to be an access point, okay. So the infrastructure mode Wi-Fi networks are used in public spaces such as the cafe, such as the libraries, the airports, okay, to enable mobile users to connect to the internet, okay. It is your way to connect to the internet if you need to connect to one network, okay. So they are also used in offices and homes to provide network connectivity without the need of expensive cabling to be installed. Okay, so we can, okay, it is a good way, okay, to have connections, okay, for all without any cables, without any, just with wireless communications, okay. Just you need this access point to be connected to the wired network, okay, and this network will be, okay, propagated, okay, over an area, okay, an area of coverage. So, for example, in an office setting, a single Wi-Fi access point in a meeting room can provide a network connection for all participants in a meeting, whereas a single wired connection can be used easily by only one person. So you can see the difference when you have just one wired, okay, connection. You can create from this one connection an access point to many others, okay, to connect wirelessly, okay. So is it clear? Do you have any question? Okay. Okay, so let's move now to the attenuation and interference. So as you know, the lower signal strength results in a lower data rate. Okay, when you have lower signal strength, okay, so the rate will be lower, okay, because the lower strength signal is more sensitive to interference. Okay, so with signal attenuation, the effective data rate reduces with distance from the access point. The case of an ad hoc network with distance from other stations, okay? As you are far from the station, so the communication will be poor, okay? Will be difficult, okay? And the data rate will be poor and the connections and all the whole connections will be poor, okay? Physical barriers also, such as partitions and walls, further reduce the maximum rate possible at a given distance from the access point, okay? So all these, okay, barriers, obstacles, okay, that you have in your building, that you have in your home, for example, so will reduce, okay, the maximum rate possible given this distance from the access point, okay? Okay, so look at this table. So in this table, it will show the typical effect of physical barriers within a building. Okay, so you can see if you are in the lift. Okay, so you will have very poor connection. Okay, the signal is very low and it will result on the data rate. So you will have just 3.3 megabits per second. Okay, but if you have in the stairwell, okay, so several thin partition walls, concrete walls, several doors here because we have some metal. Okay, so this metal will play the role of obstacles here. Okay, but when you have some doors, okay, so the strength of the signal is good and you will attain more than 6.8 megabit per second. If you have in the second floor lobby, sorry, so you have several thin partition walls, several doors, okay, and you will have very good strength, okay, of the signal. So you can reach 9.8 megabit per second. So it will differ, okay, from one floor to another, from one building to another. Okay, it is related to the materials that the building is constructed with. It is to the thickness of the partitions and of the walls, of the doors. Okay, all this will have some impact on the signal strength and on the data rate. Okay, so this is all about the Wi-Fi. Okay, so let's summarize. So the Wi-Fi can operate in ad hoc mode or infrastructure mode. So examples of ad hoc mode in the VANET and the MANET. Okay, so it is the vehicular ad hoc and the mobile ad hoc networks. Okay, they can communicate directly without any central station, without any intermediate. Okay, but in the infrastructure mode, so you will have some access point that is related to wired networks, okay, and from this wired network, okay, you will have what? You will have, okay, many participants, okay, that can benefit from this one connection. Okay, so this is the example of cafe, this is the example of libraries, of airports, okay, of places when you have, okay, some wired network, and from this wired network we can create wireless communication networks, okay, using an access point. Is it clear? So this is all about the Wi-Fi. Okay, is it clear? Do you have any question? Okay, so move now to the Bluetooth technology. So in the Bluetooth technology standard is part of the IEEE 802.15 family. Okay, so you can see the standard here differ from the standard of the Wi-Fi. Okay, so in the Wi-Fi we have 802.11. Okay, .11, and we will have many family. It is the same here. We have many family for the Bluetooth standard. Okay, but it is for very small wireless ranges, normally from less than 1 meter to 100. Okay, maximum. Okay, so the driving force for the development of the Bluetooth standard was to eliminate the need for connecting wires between small local devices such as keyboards, monitors, printers, okay, PDAs, phones, headsets, okay, all this because you need to connect to some devices that are very, okay, close to you. So this technology was created, okay, for this purpose, okay. So this was already possible using infrared technology, okay. In the past, we used the infrared technology, as you remember. If you remember this technology, we can connect, we can exchange data, okay, using this infrared technology. But the requirement for line of sight positioning between the communicating devices limits the infrared usefulness. Okay, this is why this infrared it is not used, because we need this line. Okay, imagine that this is your mobile and this is the mobile of your friend, and you need to exchange some data, some images by infrared. So you need a line of sight. Sorry, it is called the line of sight. If you have anything that here, okay, just a small thing, this line of sight will be interrupted, and it is not very useful. Okay, so for this reason, okay, the Bluetooth, okay, uses the radio waves. Bluetooth devices can communicate with each other without a line of sight. We don't need to have a line of sight, just a coverage. Okay. So when switch on, is Bluetooth device locates others by transmitting a signal that alerts other Bluetooth devices in the neighborhood. Okay, so this is how you can connect. How you can connect? So you can once you open your Bluetooth, so your device will transmit some messages to the others, okay, device, Bluetooth devices in the neighborhood, in its coverage. Okay, any two Bluetooth enabled devices can form an ad hoc connection. What does it mean here, an ad hoc connection? Do you remember the ad hoc mode of the Wi-Fi? Here we will have an ad hoc connection. Okay, so what does it mean here, an ad hoc connection? What does it mean, ad hoc connection? Tell me. Yeah, good, Sadia. They will communicate directly without any central station, without any intermediate, okay, between them. Okay, and establish a personal area network, a PAN, with a small number of other devices, each being identified by its MAC address. What is the MAC address here? Okay, we see that we have two modes of communications, using the MAC address or using the IP address. So when we are in local network, okay, so we can use just the MAC address, the physical address, okay, the MAC address or the physical address, okay, that can be used using any switch. But when you are connecting to some wide area networks, okay, like the internet, the other networks with another branch from the university, etc. Okay, so you need to use some IP address. Okay, and here because we form a small, okay, and the local area network. So we can use just your MAC address. It is your physical address. The physical address is the address of your device. Okay, once you have a mobile or a laptop or whatever, okay, the printer, so you have the MAC address. It is a unique number, okay. So such a small network, often known as piconet, is shown in figure 10. This is the piconet. So okay, so you will have each piconet, okay, will have this, will communicate, okay, with others, okay, using this technology. So one device in the piconet becomes the master. Here, when you have many devices that will communicate with each other using the Bluetooth now. So you will need some master unit, and the others act as slaves. Okay. So responding to commands from the master. The master unit now controls all aspects of the communication within the piconet. Okay. It will design dedicated time slots when each slave can communicate. Okay. So imagine that this, okay, wishes to communicate with this one. Okay. So this Bluetooth device will connect with the master, and the master will give him the opportunity to communicate with the others. Okay, it will have some slots time, some data rate, etc. And imagine now this device wish to communicate with that one. Okay. So they cannot communicate easily because we have here a piconet. Okay, we have here many entities that wishes to communicate. Okay, so this Bluetooth device will communicate with the master, and this master will control all these communication slots. Okay, so this prevents slaves from sending data simultaneously, and is another way of organizing access control and avoiding collisions or contention between slaves for access to the master. Okay. If you connect a mobile with wireless headphones, so the master will be yes, because you can connect with your headphone. Okay. We can connect with other, for example, devices. Okay, so your mobile will control these different slaves. Okay, these different devices and these different communications. Okay, between the others. Okay, is it clear now? Is it clear about the Bluetooth technology and the Wi-Fi? Okay, now we will move to the error detection and correction now. So once we have done the sampling and the quantization, okay, so we will have a stream of bits 0, 1, 1, 0, for example, 1, 0, 0, 1, 1, etc. So this stream of bits needs to be transmitted to the transmitter. Okay, this is the receiver. Sorry, this is the receiver, from the transmitter to the receiver. Okay, so all the transmitted data signals suffer from the occasional error. What is the occasional error here? The 0 is interpreted as a 1 and the 1 is interpreted as a 0. Okay, so many methods are used to detect and correct these errors, and among them we have the automatic repeat request, the ARQ protocol. We have the forward error correction code, the FEC, and we have the parity checks. Okay, is it clear? So what is the type of errors? Okay, so the 0 is misinterpreted as a 1 and the 1 is misinterpreted as a 0. Okay, so we need some protocols, some codes that detect these errors and correct them. Okay, so let's begin by the error connection by the automatic repeat request protocol, the ARQ protocol. Okay, So here the sender waits for an acknowledgement frame from the receiver. If this is not received, then the frame is retransmitted. Okay, and this protocol is used by the Wi-Fi. When you use the Wi-Fi for communications, okay, so there are some acknowledgement between the receiver and the transmitter and the receiver. Okay. Move now to the forward error correction code. So another method now may be for the speaker to repeat everything he says a few times so that there is a better chance that the listener will get the message. Okay, so I will repeat. This is the error connection. It is another method that can be used. Okay, to in which the speaker will repeat all that he says. Okay, for a few times. Why? Because once, okay, the listener lose some okay words, it will, okay, catch these words. Okay, it will get it. Okay, so the listener compares with the speaker says in each repetition and picks a version that seems most correct. Okay, so from the first time the listener will get some information, from the second time other formations, from the third time, etc. So until after some number of times he will get the right message. Okay, so it is, okay, it will deal with the repetition. Here we will use the repetition to correction. Okay, the repetition. Okay, so repeating a message several times increases the bit rate required for a transmission. Okay, so for example, the original data will be 100111101. So may it have each individual bit transmitted 3 times. So you can see here it will be 3 times. Okay, so it will be 111 000 000 111 111 111. Okay, 000 and 111. So this is the right message. Once I see that in these 3-1, okay, in these zeros I have 1. Okay, so there are some problem here. Okay, even if the 1 here is 0 or these zeros are 1s. Okay, so I need to check here. Okay, here no, it is not okay. This is not okay because I have different digits. Okay, so I need to check which digit is the right one and which is the wrong one. Okay, so we can assume that the italicized red bits are in error, but and reconstruct the original data using a simple best of 3 algorithm. Okay, we can use here the best of 3 algorithm. Okay, move now to the parity check. Okay, so the first one is to by acknowledgement. Once I receive the acknowledgement, I will send you again. Once the transmitter does not receive any acknowledgement, so it will retransmit. Okay, just one. For the repetition or for the FEC, we will use the repetition. Okay, so we will repeat the signal 3 times, 4 times, 5 times, etc. Okay, and we will use some algorithms to check or to detect the errors. Okay, for the parity check now, it is the simplest idea in error control coding, which forms the basis of a number of more advanced techniques. Okay, it is the simplest idea in error control coding, which forms the basis of a number of more advanced techniques. So the principle of the parity check is that for a given block of bits, so you have now a given block of bits, you add one further bit. It is called the parity bit, which is chosen to be 1 or 0, as to ensure that the total number of ones in the block of bits, including the parity bit, is an even number. Okay? So if you have, you need to have in each block an even number of ones. Okay? If you have 7 ones, okay? So the parity will be 1. Why? Because I will get 8 ones, so this is an even number. If I have 5 ones, so the parity here, sorry, if I have 6 ones, so the parity will be 0. Why? Because already I have even number of ones. Okay, so this is the parity bit. Okay, so the parity checking can be done for odd parity. Any single error in the block will now make the parity of the block of bits odd, because an error changes either 1 to 0 or 0 to 1. So in either case, the number of ones in the block changes from even to odd. Okay, so the receiver can therefore just count the number of ones now in the received block of bits. If the number is odd, it knows that has been at least one error. Okay, we will see that by look here. So the system usually operates with low error rates, meaning that the probability of there being more than one error in a block of bits is small. So a parity check is a good way of being reasonably confident and there are no errors. So look at this example. A simple example of the use of parity is to add check digits, okay, to a 7-bit ASQ code. So after adding, each symbol is represented, okay, using 8 bits with even parity. So look now, which of the following might be valid code words using even parity? So tell me, for the A, it is valid or invalid? For the A, tell me, A valid or invalid? How you can say valid or invalid? How you can answer this question? You need to count the number of ones. You need to count the number of ones. How many ones you have in A? How many ones? We have 1, 2, 3, and 4. Okay, 4. 4, it is an even number. 4 ones. 4 is an even number, so it is valid. Okay, valid. Why? Because I have an even number. Okay, look now to the B. For B, it is valid or invalid? B. For the B now. What about the B? Good, Sadia. Why? Good, Ahmed. Why it is invalid? Yeah, odd number, because odd number of ones. Look, 1, 2, and 3. We have 3 ones, so it is not, it is an odd number of ones, so it is invalid. Okay, here we have invalid. For the C, 1, 2, 3, 4, 5. So it is valid or invalid? Valid? Yes, good. Invalid. Good. It is invalid because we have an odd number of ones. For the D, 1, 2, 3, 4, 5, 6. Valid or invalid? For the D, valid. Good. Why it is valid? Because we have an even number of ones. So this is what is called the parity check. Okay? This is what is called the parity check. Okay. Invalid, 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 invalid. Okay. Okay, so now we need not just to detect if there is an error or not, we can correct this error. Okay. So the parity check If it was odd parity check, then it would be invalid if no of one or even. If the number of ones are no, it is not odd parity check. If you have an odd number of ones, it will be invalid. If you know if the number of ones is even, it is valid. Okay. We don't have odd parity and even parity. No, we have only the even parity. We have only the even number of ones. Okay, so if it is even, it is good. It is not even, it is odd, so it is not valid. Okay, so this error detection is useful, but it would be good to be able to correct now. It is not only to detect, okay, if there is an error or not, it can be to correct errors. Okay, so figure 3.36, this one, shows a sample example of one way this can be achieved using 7 multiplied by 5 message block with even parity digits. Okay, even parity digits. So the message digits are laid out in a rectangular block code with parity checks, all even or odd, for each row and column. Okay, so this row, the last column is for parity check, and the last row for parity check. Okay, so this is for rows, and this is for columns and for rows. Okay, so any one error will cause the parity check to fail in one row and one column. Okay, any here changes in this. Okay, so it will reflect some errors in the parity check. Okay, of the columns and errors. Okay, so knowing now which row and which column have failed provides the coordinates that identify the bit that is in error, so it can be corrected. Okay, so this is how we can correct when we have one error in some columns with one error in some rows. Okay, so the intersection of this row and this column, okay, will show you the wrong digit. Okay, so if the bit now is 1, it should be changed to 0, and if it is 0, it should be changed to 1. So let's have a look at this example. Okay, so this is a 7 by 5 block with even parity checks, as in the above example, is received as following. Okay, so this is the received block. Which bit is in error? Which bit? Which bit now? You have received this block, okay, and you need to check if there is an error or not, and to correct this error. Okay, so in the first you need to check every rows. Okay, row by row. Okay, and after that you need to check every column by column, and the intersection of the of the error, okay, of the column by row, you will have the bit, erroneous bit. Okay, so let's start. Here, 1, 2, 3, 4, so it is good. Okay, an even number. The second, 1, 2, 3, 4, so is good. The third, 1, 2, 3, so here we have some problem. It is not good. Okay, here it is invalid. Okay, 1, 2, 3, 4 is good. 1, 2 is good. 1, 2, 3, 4 is good. Okay, so I have the third column, the third row that contain an erroneous bit. I don't know till now. I don't know which is the erroneous bit. Okay, just I know that this row is invalid. Now move to the columns. I need now to check. So I have here 1, 2, 3, 4 is good. For this one, 1, 2 is good. Okay, 1, 2 is good. Okay, 1, 2, 3. So this is an invalid column. This one. Okay. 1, 2 is good. 1, 2, 3, 4 good. 1, 2 good. And 1, 2 is good. Okay. So we have this erroneous. This is the erroneous. Okay. Bit. Once I change this 0 by 1, okay, I will get all columns and all rows valid. Okay, so let's check. Imagine that this is a 1 here. It is not a 0. This is a 1. So 1, 2, 3, 4 will be good, valid. And 1, 2, 3, 4 will be valid. So this is the erroneous bit. Okay. So the parity check is correct for all rows except the row 3 and the column 4. So this bit is in error. Okay, this is the error. And we can change this 0 by 1, okay, and we will get the right code, okay, at the receiver. Is it clear? Clear? Yeah, the erroneous will be the intersection between the third row and the fourth column. Clear? Clear? Okay, so move now to the security, the last part of this meeting. So the wireless networks transmit data over a medium that is shared by everyone. Okay, so anyone with compatible receiver is able to eavesdrop or spy on the radio signals being sent. Okay, because we use a shared area, we use a shared medium. Okay, so any eavesdropper or spy, okay, can have, okay, can do some, okay, attacks on this data. So one column used security mechanism for this networks is the encryption. Okay, and you can see that in your Wi-Fi devices. It is web, okay, or it is WAP, okay, or WAP, okay, connect security connection. Okay, so it is and developed over the years. Okay, so the idea of encryption is to take the information you wish. Okay, what does it mean, encryption? So the encryption is to transform the plain text, okay, your message, it is called the plain text, and transform it into a different form called ciphertext, which is not understandable, okay, which cannot be readable, okay, such that only the people who are supposed to receive the information are able to reverse the transformation and recover the plain text. Okay, so this is your plain text, for example, hello here. Okay, hello, this word will be transmitted, okay, encrypted, will be encrypted, be ciphered by, for example, E, V, R, T, for example. Okay, so it is not understandable. I can use many algorithms for encryption. Okay, so we can here, for example, use some translation in the words. Okay, by some number. Okay, so this transfer and how we can recover. So only the receiver know the procedure of this encryption so he can, or it can decrypt, okay, decrypt these text and have the plain text. Okay, so a transformation process for converting plain text to ciphertext is called encryption, and the inverse process is called decryption. Okay, so what does it mean? Encryption is the conversion from plain text to ciphertext. What is the decryption? Is from ciphertext to plain text. Okay, so every encryption has the security benefits of confidentiality, integrity, and authentication. Okay, it will ensure all the security requirements. Okay, So what does it mean now, confidentiality? Confidentiality, when a message is encrypted using a particular key, it can be decrypted only if the same key is used. So this feature ensures that the messages are confidential between the sender and the receiver. Okay, it is confidential. Okay, it is confidential. And so confidentiality is in fact the fact or the act of keeping a message confidential by encryption decryption using a confidential key. If the attacker can guess the key so that the message can be read, and this kind of attack is called brute force attack. What is the brute force attack? It is a kind of attack that when the attacker gets the key. Okay, so this is the reason why in encryption you need to use a difficult key. Okay, because the hacker, there are many algorithms that can guess, okay, your key if it is simple. Okay, therefore the number of possible keys that can be used by an encryption function is an important factor that affects its strength. Okay, so you can have a strength, okay, method encryption while you have 128, okay, key. Okay, when you have a key that contains 128, okay, bits, so you will have a strength encryption. Why? Because to guess this number you need 2 power 128 combinations. It is a huge number. Okay, so if the number of possible keys is sufficiently large, okay, sufficiently large, it contains here, for example, 128, okay, completely random and impossible to guess, okay, then brute force attacks become much more difficult. Okay, it is a difficult task for these algorithms to guess. It is not like your phone, it is different. This is the communication, okay? So in the communication medium, you don't have some devices to be blocked or whatever, it is just information that are sent between receiver and transmitter and receiver. The man in the middle or this attacker or whatever, okay, can have this data and try it's your best, or it's to guess the key to have this data. Okay, so it is not related to it is not a device that will be blocked, or it is the data itself. Okay, integrity. Now what does it mean, integrity? Now confidentiality deals with the right person. It will be only the right one that will open this message. Okay, it is destined to do this message to this person, so only this person will open this this message. Now for the integrity. So the integrity is the prevention of messages from being modified, okay, without the receiver knowledge. So imagine that you receive an email from someone, okay, how you can be sure that this email does not be changed, okay, and or modified, okay. So you have some keys. So encryption can prevent messages from being modified without the receiver's knowledge, and the only way for a man in the middle attacker to modify a message is to decrypt it. So once we have this brute force attack, so we can guess the key, and once I get the plain text, I can modify this text. So this is the man in the middle attack, okay? But this is impossible only if the attacker knows the key, okay? So we need to know the key to have some type of attack. So any attempt to modify the encrypted text would cause the decryption process to produce a meaningless message, which would alert the receiver that someone had tried to tamper with the transmission. Okay. So without decryption, the ciphertext, any modification on the ciphertext, okay, when the receiver receive this message, so it will decrypt this message, and once he gets unmeaningful, okay, there are no meaning for this message, so he will automatically understand that there are some men in the middle that wish to modify, to alter, to temper this message, but he cannot because the message is already encrypted. Okay, so he need to decrypt in the first and to change, and after that he will encrypt again and send to the receiver. Okay, so by this way we break the integrity for this message. Okay, so the man in the middle attack is a malicious user secretly interposed between the sender and the receiver, which modifies or deletes information. Okay. Authentication now, encryption can also contribute to authentication. How it can contribute? So the authentication is the process of proving the identities of the sender and the receiver. Okay. So to do this, the sender and the receiver exchange some predefined messages that are encrypted using a key known only to them. It is an exchange called a protocol or a security protocol. Okay, so this is a security protocol. This is called a security protocol. Okay, so do you have any question? Thank you for your attendance, for your interaction, for your participation, and feel free to ask questions if you have any questions.